Hello everyone and welcome to my talk about IDF networking. My name is Cermak and I'm going to present a talk about best practices in handling interfaces, events and disconnect in IDF networking. So I will talk about networking layers in IDF. I will describe what we have in IDF around the TCP/IP stack and how we can use it, how we can configure that. Then I will give some examples about applications, like different various settings of the event handling from different layers. And at the end, I will conclude with tips and actions that we recommend how users could set up and configure IDF networking and how disconnects and different errors could be handled. Before we start, let's talk about the motivation for this talk. Because networking in IDF is probably the first thing that everyone would use. And we have plentiful of examples of using networking for various components, various networking libraries. One example is here the MQTT over TLS. We have an example for that. Everyone can start it, everyone can run it, and it works, it publishes. So that should be no problem. But yeah, the problems that users could encounter with this specific example and with other networking applications is that we could get disconnected from the Wi-Fi, from the network, or from the MQTT broker. We could see that the endpoint is not available. In our case, the MQTT broker is offline. We could even suffer from out-of-order delivery of different events from Wi-Fi and IP layer. So we could get a disconnection from Wi-Fi and at the same time connection to IP, so getting the valid IP address. And that's due to the asynchronicity of the things of the network and events and different layers. We also know that TCP is not real time, but sometimes we forget, and we forget that TCP takes care of resending data, retrying, backing off. So sometimes takes some time until an endpoint is considered disconnected. About the networking layers in IDF, so we all know that the TCP/IP stack that we use in IDF is LWIP, so the most common TCP/IP stack that is used in other embedded platforms too. LWIP is also called lightweight IP, and around this TCP/IP stack we have several layers which are IDF specific, so drivers for Wi-Fi, Ethernet, PPPoS, that is clear. We have this component called ESP-NetIF. I will talk about it in more details later. It is used to connect or couple this TCP/IP stack to drivers and to take care of initialization and sending and posting events. I would also like to mention this VFS or socket layer because we not only support networking sockets, but we could also VFS stands for virtual file system. So some other file system sockets, some other file system descriptors that could be used to interact with networking sockets. About the layers, we already said that we have drivers here. We have the TCP/IP stack here, which in itself has some modules like network interface, row API, some applications, socket API, and up here we have the application libraries. So we already talked about MQTT. We have others HTTP WebSocket, ASIO, and many others are available. Around the TCP/IP stack, from both sides, you can see this ESP-NetIF. So the ESP-NetIF layer here takes care of routing the network interfaces to drivers, and here it actually looks at some applications like DHCP servers, DHCP client, DNS, and talks to IDF system to actually keep it updated and actual. Also, I already talked about VFS, virtual file system. So the socket API that we use from application libraries are not LWIP sockets, but there is a thin layer that helps us working with other sockets than networking sockets. So what is really specific to IDF platform? How is it different from other networking programming? So to answer that, we will have to look at what the application that we are talking about, what it really does. So the common use cases is that we use socket layer programming, or we could use some generic network library that's available for many other platforms, including host platforms, Linux, Windows, and it's also available for Espressif chips. Or we could have like IDF component directly. So this is probably the most common use case that our customers do. ESP, MQTT, WebSocket client, and others. It is also possible to use LWIP row API, which is not recommended and it is not very scalable, but it is still possible. As for the environment and complexity, we have to think about how responsive our application would be if it's really something very conservative, an application which really relies on TCP layer to reconnect, retry, and make the connection stable again, or if we want something more real-time, or usually what it is something in between. So what our users typically want, they still want TCP, but they want the TCP that's somehow responsive, that the application is somehow alive, that if something is not available, we just bail out after a couple of seconds, not after minutes or hours. As for the complexity in terms of network interfaces, the most typical use case is that we have one single network interface, usually Wi-Fi station, and we just use that interface only. We could have multiple network interfaces with or without an interaction between them. The typical use case here is that we have Wi-Fi, at the same time we have an Ethernet connection, and at the same time we have a cellular network connection. And all these interfaces have different priorities. So if we have all of them up and running, we usually use Ethernet, preferably use Ethernet or Wi-Fi. If Wi-Fi is down and Ethernet is down, then we go with the cellular network connection over PPP or PPP over serial. So now, how the IDF platform is different. So we need to be aware of that, of the fact that it's a really embedded target and we have limited resources. So number of sockets, buffer sizes, memory, performance. We are in embedded space. So network programming in IDF. We have to be aware of this fact. Then number one is events. In IDF we have this event, this component called ESP event. So For networking, we could receive events from different layers, from driver, from link layer, from LWIP, from ESP-NetIF. Second point, interfaces. Already said that we have this ESP-NetIF component that is used to as a wrapper around network interfaces, and I will talk about it later with a lot of examples. And also the last point is the networking API, which usually and preferably is a socket API or some network library which uses socket API behind the scenes. But at this point, we have to be aware of the fact that these are not standard sockets, these are LWIP sockets. So there are some subtle differences between classic, like common Unix or Linux or Windows sockets and LWIP sockets. So let's jump to the first example and look at the events. So in the motivation slide, I talked about this MQTT over TLS example, and if what happens if we get disconnected from Ethernet. So let's run this example. I have already flashed the board, so let's just run the monitor. As you can see, this is the standard Ethernet kit, and it connects to the network and keeps publishing. Now, if I remove the Ethernet cable, we should get a disconnection. So as you can see, Ethernet link is down here, and after some time, we could probably get a lost IP event. Yes, when I reconnect, we could get a link up event here, and after some time, we get an IP address and got reconnected to the MQTT broker again. And then after reconnection, as you can see, it tried to catch up with publishes and try to publish more frequently. So let's look at the code, what it does. As I said, this is the most default MQTT example that we have in IDF, but I have added this while loop, and I have also added the event handler registration. By default, we look at Ethernet events. I think this is also part of the IDF example. So look at the Ethernet events and look at all of them. So we saw that the Ethernet link was down and was up. So that part worked okay. As for the IP events, and this IP layer, this comes from ESP-NetIF. So we typically also look at this GAT IP, and again, this listening to this event is also in the default example. But what I have added, I have also added this lost IP event. So from both driver level, from the Ethernet, we get both events disconnect and connect, and from IP level, we get both symmetrical events, GAT IP and lost IP, as we could see here. So link up, link down. Link up was here after we reconnected. Yes, here, and we got lost IP here, and another got IP here with the IP address. And I have also, as I said, I have added this this publishing mechanism, this never-ending loop that keeps indefinitely publishing some data just for the purpose of the demonstration. So let's jump back to the presentation. What we had, and come up with some recommendations. So it's always good to listen to events from drivers. Here we had events from the Ethernet, so we had both events from connection and disconnection, the Ethernet driver. But we could also listen for all of the IP level events, so not only got IP but also lost IP. You might have noticed that the lost IP event came a couple of seconds after we got disconnected. This is why there is a lost IP timer in ESP.NET-IF, and it's configurable. I have set it to 10 seconds for this example, just to demonstrate how it works. But by default, it is set to 2 minutes. And of course, we have to watch for events from the networking library itself. And if you remember, we got disconnection events and error events from the MQTT library as well. But this is really specific to the networking library that we use. So the questions that we have to ask is, does it make sense to keep sending and receiving if we are disconnected? So in other words, do we have to publish even if we are disconnected from the link layer? And does it make sense to keep trying to reconnect to MQTT even if the link layer is down? This is how the MQTT library works by default, because it has no knowledge about events from drivers. So even if the Ethernet driver is disconnected or the link is down, it always tries to reconnect, it fails, and then after some time it tries again. So usually the answers to these two questions are no, and this is basically the like our common recommendation that if there is no real intention for that, just publish or send or work with the network library only if the link layer is okay, if we are connected. And if we don't have to, if it's not too much trouble, we don't have to reconnect if the link layer is down. So what other tips we have? So we could use some keep alive mechanism. MQTT protocol itself has it, and the library in itself does that as well. So this is very useful. If we use some protocol that doesn't have it, TCP itself has a keep alive mechanism, so this could be easily set up and configured using socket options. So let's go to the next example. The next example will be about interfaces. So we'll be mainly talking about ESP.NET-IF and about like two interfaces that I have created just for the purpose of this demonstration, and how we are able to actually route packets or choose the preferred path the packets would go. So the default network interface, the default gateway. So let's jump again to the command prompt, and yeah, for this I wouldn't use Ethernet kit, but just very basic W room kit, so dev kit C. Again, it's pre-configured, and it has no connection, no external Ethernet, nothing. So it uses just Wi-Fi, nothing else. But let's take a look at this example. So as you can see, we got two IP addresses from two different ranges. So from this interface, which is the station, which is the default one, It connects to our network in the office, to our Espressif network. So it got this IP address, but it also got another IP address from this range, and 192.168.3, and the name of the interface is called Wi-Fi access point with DHCP client. And then after it got these two IP addresses on these two interfaces, it then there is HTTP GET performed for some address. I will show you quickly the code. So let's see what we have here. So this is the again modified soft access point example, again from IDF. So this is what I have just mentioned. So this is the URL. We are trying to connect or perform a get HTTP operation on http bin.org, and we do it periodically, every 5 seconds. And I've already said that we have two interfaces. So let's look at how these two interfaces are being initialized. We already mentioned that we have this board has only Wi-Fi, and this Wi-Fi is enabled and started in this mode access point plus station. But this is the Wi-Fi. This is the driver level. What about network interfaces? We run the Wi-Fi in access point plus Wi-Fi, but we'll have to initialize two interfaces, one for station and one for access point. As you can see, we initialize or we create the default Wi-Fi station. We are using the default API to create that, but the default Wi-Fi access point is commented out. So we have the default station, but as for the access point, it's not default. And let's see how is it created. So we create the ESP NetIF Wi-Fi for Wi-Fi access point. That's the same as the thing that we would have done with this create default Wi-Fi, but with this configuration. And again, this configuration is something what matters. So this configuration, and again, this line is commented out, so it does not create this default Wi-Fi access point, but it creates the default Wi-Fi station. So that's the most interesting part, because we are actually initializing the access point with the configuration which is almost the same as the configuration for station. So we have a station or an interface, network interface that behaves like a Wi-Fi station, but it runs on a Wi-Fi access point. One important thing that I will mention in the comments is that if we are configuring the interface key, this has to be a unique string, unique name. So we wouldn't just create it. It wouldn't work if we just leave it as it. We have to update the interface key. We could also update the interface description. It doesn't matter, but it's nice to call it what it really is. In this case, this is the Wi-Fi access point with the HCP client. And one important thing is the routing priority, which we set to 101. So let's look at what is the definition of the default Wi-Fi station and what is their routing priority. So it's 100. So this is this priority is higher. So the access point, this access point that we create has higher routing priority. So all the traffic that goes outside of our network should go via this access point. So let's look again what we have. So we created this access point that got this IP address, and we are calling HTTP GET to some address which is somewhere in the internet. So we need to connect to the internet, but not via station, not via our Espressif network with this. We need to connect to Wi-Fi access point. So how does it work? Because this interface has more priority. Let's start it again so that we have some we see what's going on, what's happening. So again, we got these two IP addresses, and we are getting these HTTP events. Now I have another board here, and this one is an Ethernet kit, and this Ethernet kit is the counterpart to this access point. So on this board, I actually run a Wi-Fi station that has the HCP server. So this board actually takes care of assigning this access point, this address. And at the same time, you can see that this is Ethernet kit. So and it has IP routing enabled. So it passes this data from the Wi-Fi station, which provides the address to this board which we have, and pass it to the Ethernet interface. So in this case, we are actually able to connect to internet. If I remove if I remove the Ethernet cable here, we should get a disconnection failure. Hopefully, after some time, yeah, we get it here. So failed to create a new connection. So now the default routing is still over the access point, but we have no means to connect to the internet in that way. Now, if I remove or replace this board completely and attach a default station, that's the basic default station that we have. Let's look what's happening. So this station actually joined the network, and now it started working. Why? Because it has no connection to Ethernet either. So it's just a stupid default Wi-Fi station which has no connectivity whatsoever. The reason for that is very simple. Because this routing priority is higher, since it's higher, it routes traffic only if both of these interfaces are up. But I have a condition here down below that if the IP address is a 0, we just set the link down to this access point, so the traffic could easily go to the default station mode. So again to the internet. So in this way, in this case, if we remove the connection, but at the same time we got the interface down, then we are still able to connect via the second interface. So let's jump back to the presentation and see what information we have learned about ESP-NetIF or about the wrapper to network interfaces. So we actually suggest or recommend to use default settings, default configuration wherever it is possible. If we want to have multiple instances of the same config, just be aware that we need to update this interface key. This is the unique name of the interface, and we are not allowed to add two interfaces with the same interface key. This point is very useful for Ethernet interfaces because we can have as many Ethernet interfaces as we like, because we could add Ethernets, SPI Ethernets together with one internal Ethernet for ESP32 only, for other devices, SPI Ethernet, and we can reuse the configuration for the default Ethernet, but we need to update the name or the key of the ESP-NetIF. So when we use the default config, we and we need to update something. We typically should update this inherent configuration, because the configuration of ESP-NetIF is really complex. There is a driver-specific configuration and network stack-related configuration, but this part is really for expert users. What users typically update is just this basic inherent default configuration, and then we update some specific items. And the most common fields to update are this IP info. So, and this is very useful for access point, or for those interfaces that run the HCP server, because here we can easily define ranges. I already said that interface key needs to be unique, needs to update that, and routing priority. So we need to set up the rules which interface would be the default if all of them are active, up and running. So we can look at the ESP-NetIF as a toolbox, so some set of building blocks that we could construct different networking interfaces in different manner, using some default configuration and updating just some parts. So this is about interfaces, and the last point I wanted to mention is about socket API, or API in general, and which is basically the recommended one is the socket. So here I am going to run an TCP client example, and I'm going to talk about connection, timeout with connection, because LWIP sockets, this is again one of the differences. For example, with Linux sockets, for the blocking sockets, we don't, or LWIP does not support any timeout for the blocking sockets. So, but there are ways to make the connection fail after some timeout. And I would like also to demonstrate something about this custom event file descriptor to unblock a select which is blocked on something, and perhaps talk about some more LWIPs, TCP/IP settings, so that connection to something that's not there could fail really quickly. So let's again open the example, and for that I'm again going to reconnect to the Ethernet kit, as you can see, and in this case I'm afraid I would need to flash and monitor, because there was that's probably the previous example on this Ethernet kit. So let's wait until it flashes and connects, and let's see what we have. So it connects to the Ethernet, socket is created and connecting to 1, 2, 3, 4. And now let's disconnect the wire, and as you can see, the link is down, and we got this message disconnected and exiting. So let's again jump to the code and see what we have here. So this is again from the default TCP client example. But instead of connecting the way the TCP client does, so connecting with the blocking socket, we set the socket to the non-blocking mode and try to connect. And if in progress, we just call select. But we don't call the select just on this single socket, but we have another file descriptor here. So let's look at this disconnect FD, what it does. So that's a global variable, which we actually write into in case we got a disconnected event from the Ethernet. Because again, we ran this example on the Ethernet kit. So we actually watch for this file descriptor as well as we do for the socket, and try call select on that. And if the select returned, so this is the blocking call, and it does whenever something in this file or in this file changed. So in our case, it was disconnected exiting. So we got here, and we exited from select, and this is the message that was printed because the disconnect file descriptor was actually set. So in that case, we just close the socket and do after close. So this is very useful to inform, let's say, a task that calls select and does select on multiple, not only one socket, but we could have many more sockets that we care about. But this way we can inform the select to return immediately and watch for this custom file descriptor to see if something unexpected has happened, for example, on the board or something else. This demonstration actually showed the disconnection, but in this specific case, it's not so needed because the select would return as well, because the Ethernet link down actually sets the network interface down, and in this case, the network interface in LWIP would know about that, and select would return even if we didn't use file descriptor. But this is just for the demonstration that we could use this event file descriptor for some other means to communicate, or if we use some custom network interface. What I also wanted to show you is that this connection, even if we don't want to spend too much time on connection, we can update some TCP parameters. So I have prepared here the TCP, some TCP parameters of LWIP. So maximum number of retransmission of SYN segments, and the initial retransmit timeout time. The default is 3 seconds, but in IDF the default is 1.5 seconds. These options are generally available in our kconfig, so we can update it there as well. But here, for the simplicity, I could update it directly, just updating it simply to avoid the need to rebuild the entire IDF. So we will just rebuild the LWIP component, And as you can see, I have reconnected the Ethernet wire, and once it builds, it would flash the program, and hopefully it will disconnect by itself. So if we look again at the numbers, it should retry only 3 times and initially wait only 500 milliseconds before the initial retransmission. So yeah, we got here, so select return, and we got an error that the connection actually failed. So this is the way we can also adjust parameters of the TCP protocol itself, so to make the TCP a little bit more responsive. So I'm not saying that these numbers are really something that we should use or we should stick with. Probably the initial retransmit timeout of 1500 milliseconds is good enough. So the IDF default is probably fine. We could adjust the maximum retransmit of SYN segments, or also the data segments. But basically, in most cases, the IDF defaults are just fine. So let's return to return to the presentation, and let's see what we have learned when showing this example. So about socket API, I've already mentioned that these are LWIP sockets. So we need to be aware that there are certain differences. So please read the documentation in IDF docs about LWIP. It's pretty well described. There are certain differences, mainly related to closing sockets from another thread, shutting down sockets, and other. I've already mentioned the connection timeout. So another point, if you like to handle timeouts for connection, you need to switch the sockets to non-blocking mode and check for or use select to actually check for either timeout or connection succeeded or failure. We also could use event file descriptors to pass additional information either about disconnection or about something, some other signal to a blocked select call. And if we are using some custom network interface implementation, if we set up our own network interface implementation with our own driver, we need to be sure that we always set the network interface down if the physical layer disconnects. In that case, we could be sure that the LWIP, the TCP/IP stack, always know that something happens on the physical layer and could report and failure. So let me just conclude with what I have to say about all of these three examples. Already said that we in IDF use LWIP, so there are certain things, certain stuff in networking configuration that is specific to LWIP. So already mentioned something about sockets. There are some other parts like DNS or output buffers and stuff like that. But please check the documentation for that. It is very important. But in general, in the common use cases, LWIP sockets behave almost like the normal common Linux sockets. About performance and kind of responsiveness, liveness of the application, I have shown that it's possible to set up the TCP parameters in kconfig options. As for if we are looking for the best performance, we need to adjust buffers to maximum. And it's always good to look at our iperf example in IDF, because this is the example that's used to measure the maximum performance. It includes IRAM optimizations. It sets the input and output buffers to maximum, so it is really adjusted to generate maximum throughput, maximum performance. About keep alive, it's always good to have a mechanism that tells you that the other part is not active. So you can use TCP keep alive, you can use library or protocol specific keep alive mechanism, or even in application you can, for example, ping or check if certain address or service is active, and if not, you can send an event or this event file descriptor to take actions. About interfaces, we said that this interface key needs to be unique, and we need to be aware of the routing priority and the default network interface. In IDF now, the ESP NetIF provides an API to actually override the default NetIF to set it directly, so not based on the routing priority, but if the application has some complex rules to decide which interface should be the default one, then users are suggested to actually use this default native API. As for the events, we have shown that we have the IP events, which comes basically from the TCP/IP stack. Plus, we have also the event that comes from drivers from the physical layer, and the link layer, if the link is up or down. We could have the network library events, and the first example I have shown the event from the MQTT library, the disconnection event, or the error event. And we could also have application events, as I mentioned already. So this is all from me. Thank you for watching, and if you have any questions, please ask.